Hi, my name is Seth Luitjohan. I graduated in 2021 from Southern Illinois University in Carbondale, and I'm currently an architectural designer at Canon Design in St. Louis. Before I get started, I want to thank the Society for Modeling and Simulation International for allowing us to share our research. I would also like to thank the co-authors of this paper, Mehdi Ashayeri, professor at SIUC, and Narjes Abbasabadi, professor at UT Arlington. Both were so helpful and insightful throughout the process, and it was a pleasure working alongside them. So without further ado, I'm excited to share with you an optimization framework and tool for context-sensitive solar-driven design using cellular automata. I will briefly go over some details, some background and literature that warrant this study. Then I'll go over our developed methodology explained in detail. I'll go over results and finally discuss what can be taken away from our findings. Buildings account for over 1/3 of energy consumption and nearly 40% of CO2 emissions globally, according to the UN Environment Program. On top of this, cities continue to grow exponentially in both population and development. The United Nations projects that by 2030, cities will house 60% of the global population. To combat this, the AIA 2030 commitment calls for the architectural practice to move toward more holistic, data-driven processes by iterating and simulating design options and incorporating more renewable energy, such as solar radiation. Solar radiation is the most abundant form of energy in the world. A 2020 study found that dense cities with erratic height fluctuations possess large degrees of untapped solar energy potential. However, few frameworks exist that focus on helping the designer increase solar energy potential in these dense urban environments. Many studies have established frameworks that incorporate artificial intelligence into early stage design to explore and optimize design as a response to sustainability goals. Branching from artificial intelligence is generative design, which is a computational evolutionary system that is reflective of a specific design problem determined by the designer and has proved capable of automating some design processes with high accuracy, efficiency, and consistency. Generative design has been viewed as a paradigm shift for a long time by proving to be capable of generating complex outcomes that are generally unconceivable by humans alone, while still offering us as designers the opportunity to strike a balance between subjective preferences and more performance-based criteria. In performance-based design, environmental factors like solar radiation and daylighting are improved by simulating a building form's massing, orientation, shading devices, and so on. The iterative nature of generative design makes it an ideal early-stage design approach by allowing for rapid exploration of countless design alternatives. This provides an opportunity to find higher performing solutions when optimizing for sustainability-related objectives is demanded, for example, increasing solar energy potential. Cellular automata is a type of generative design and is a two-dimensional or three-dimensional system of cells with binary states on or off and can generate highly complex arrangements. Cellular automata was first used in architecture by John Fraser in 1995 and has since been implemented as a morphogenetic bottom-up approach where predetermined solutions are avoided as the generated outcomes are more complex and unpredictable. One main advantage of cellular automata is that its entire system is based on surrounding cells and local dynamics, which makes it suitable for context-sensitive form-finding explorations. This is worth noting because context is principal in performance-based design of dense, high-rise building areas because of the impact they have on surrounding sites. Many studies have utilized generative design techniques in developing solar-based design frameworks. genetic algorithms have commonly been used to maximize solar radiation incident by quickly iterating through thousands of design options until the optimal form is found. While this method is effective and efficient, it requires input forms from the designer, which sort of eliminates the appeal of avoiding preconceptions and predictability. Some studies have aimed to maximize solar radiation incident at neighborhood block level by addressing building height, arrangement, orientation, etc. However, these are not suitable for individual building level because they disregard the more granular and complex building form properties as they derive from context. Other studies have applied generative design algorithms to maximize solar radiation based on individual building form, but have overlooked consideration of urban context within high-rise areas. There's still a gap in the literature for maximizing solar radiation incident in urban contexts using cellular automata for building form generation. Therefore, we've developed a solar-driven form-finding framework and tool assisted by cellular automata called SDCA. The tool allows for maximization of solar radiation incident in early-stage design for increasing renewable energy potential. The tool is computationally efficient and provides suggestive volumes by addressing the surrounding morphology and their casted shadows. The findings of this research can help designers in providing suggestive building forms during the form-finding process when aiming to address low-carbon and sustainable design goals. So moving on to materials and methods. The framework developed in the study utilizes a two-step approach, first for parametrically producing an optimal volume distribution, and second, improving it for additional design applicability using cellular automata. The forms are produced based on amount of solar radiation and contextual morphology. The tool was tested in 3 major US cities to demonstrate its effectiveness and feasibility. The 3 testing sites are Chicago, Illinois, Minneapolis, Minnesota, and New York City, New York, and were chosen from Ashayeri's cool and cold climate zones. In these areas where more energy is used to heat the building, it made more sense to maximize solar radiation incident, even though the renewable solar energy could be used to heat and cool the building. All 3 sites were chosen based on unique surrounding morphologies to provide more holistic results while creating more of a challenge for the tool. The Chicago site is 3 blocks north of the Willis Tower. The Minneapolis site is surrounded by the tallest buildings in the city, and the New York City site is adjacent to 2 high-rises on the east and west side of the site. The framework takes place in Grasshopper using Ladybug for solar radiation analysis. And the first step consists of 2 types of inputs, predefined, such as EPW file based on location, surrounding context geometry, and the site boundary. The second type of input is user-defined to give more flexibility to the designer. These inputs are 3D grid granularity, analysis period to optimize for, building height, and target volume percentage of the 3D site. For example, in this graphic, it's placing voxels at 50% of the volume of the allowable volume according to the solar radiation levels. And you'll notice in this graphic that this process creates some pockets and floating voxels that might make it difficult for the designer to use. To address this, cellular automata is used to improve the form by eliminating noise. The framework utilized a cellular automata plugin for Grasshopper called Rabbit. And this step takes the output form from step 1 and specific cellular automata rules for which voxels to add or eliminate to address the anomalies and make the form more applicable for the designer. And we tested this methodology for seasonal and annual analysis periods to provide a range of results, but these analysis periods could be changed by the designer to a shorter period, even down to a specific day. We also tested the tool for 50 and 75% of the site volumes, but again, this is highly flexible according to the user's needs. And you can see how highly complex the resulting suggested forms can be, and this is a product of the voxelated medium at this finer granularity of 10 feet per voxel, as opposed to a geometry that was made up of, for example, vertex control points. And this granularity can also be defined by the user, larger or smaller, based on how much computational power you can afford, really. But it should be noted that each of these forms were generated by the tool in under 5 minutes apiece, so it is very computationally efficient. And this is a look at how the cellular automata is refining the form in step 2 after 2 generations. And it's just enough to make the forms more usable for the designer without deviating too much from the original optimized form. And finally, we validated the results to test whether or not the tool actually did its job. And we compared the resulting forms to 2 control forms based on equal volume with different distributions. The first takes up the entire site footprint, and the second control form reaches the maximum height. And while obviously the resulting forms received more radiation than the shorter control forms, every resulting form option received more radiation than the equal height control form, while it is a bit closer in kBTU per square foot. I should also mention that we used the annual forms for comparison because they were the summation of all of the analysis periods, which helped to make it a more holistic comparison. And here you can see all the performances side by side. Again, the generated forms received higher solar radiation incident in every instance, but was not as effective in some cases, particularly when 75% of the volume was generated. So moving on to discussion. This is a GIF we put together of all the results from all 12-month analysis periods. And we did this to highlight the framework's flexibility, and you can already see how this kind of graphic could be useful to the designer to gain a better understanding of how solar radiation is reaching a 3-dimensional site place throughout the year. And then on the other hand, keeping the analysis period constant but changing the target volume percentage, and you get this visual that sort of suggests a hierarchy of space in terms of solar radiation levels. So the tool is capable of providing suggestive building forms with maximum solar radiation for different sites. The methodology is flexible for the designer regarding target percentage of the site volume, height, and voxel granularity, as well as analysis period. Computational times of less than 5 minutes per form were achieved, and the main limitation of this study is that only one single parameter solar radiation incident was optimized for, while a multi-objective optimization would provide more holistic results. And in conclusion, The goal of this study was to build on past studies to develop a tool that architects can use in form finding when designing for renewable solar energy. And results show that the proposed method is capable of creating many architecturally applicable suggestive forms with improved solar radiation incident, which a designer could use to help inform their decisions. Further research could work toward implementing additional parameters, for example, daylighting and energy loads, to make a more well-rounded optimization tool. Thank you. And once again, thank you to the Society for Modeling and Simulation International for allowing us to share our study.